describe what I would like to talk about. Then there will be the mathematical setting, the results, and all this part is about the evolution of what are called vortex elements in 3D and equation. And amazingly, it is connected to a geometric object, which is the evolution of curves in 3D. That the law of the evolution is given by the curvature times the binomial. This is the very simple way of describing the geometric laws, but it's very rich in terms of the dynamics. So this will be the bulk of the talk, and depending if I either have time or not, I will speak about some specific properties of this binomial flow that are very linked to turbulence, right? Particular two interesting properties of turbulence fluids in particular, which are, they fit under the name of intermittency. It is some way of describing that the probability distributions that are behind the histograms and the time series given by velocities and things like that are not constant. Big, heavy page, which are, and then this is described by something called multifractality. And this is very much related also to some, say, describe it as geometric properties, which is the appearance of complicated sets that are made of different fractals with different dimensions. But this is mainly in the setting of the binomial form. So you are describing, in principle, say, stochastic behavior, probabilistic behavior. So you would like to say what is the universal guide description, and this universal guide is the one you see on the slide. So it's a pretty well-known guide. It's the sum of trigonometric series, where you have a parameter, which of course is time, and the say the amplitudes or the Fourier coefficients are in principle they are not stochastic, they are Gaussian in the spirit of Nikolai Stock, but they are not so easy to describe. For example, in that expression, P is rational or P is irrational makes a huge difference. Correct? So, in particular, with this kind of this guy, you can describe objects as the ones you see here, and this guy is different. For example, in the previous case, there was a parameter in n equals 3, and now it's a parameter in 4. They are different, and they are described by by using this ion and changing just this. So I don't know if I will have the time to particularly speak about this, but this is what I would like to. I mean, this for me, I really would like to describe this, the connection between, say, this part and 4, 3, 2. This is what it is not clear. For me now it's a very relevant question. I don't know what is the answer, but whatever is the answer is going to be this. This is my question. So, but before the movies, I have to show you a picture that I took on Monday. It's on the other side of the world. This is the reason why this is etc. Because the guy who was very much interested in this was Leipzig. And in fact, they want to, the way I see the result with Montelos is that we prove, or at least we did a substantial step forward, saying that the Leipzig was good. So now the movies. So, well, this is what we call a vortex filament. So this is the typical smoke ring. And it's in principle, it is you see something, but what it is probably so clear, at least to me, is what we see. We see some principal circle that it is moving with a very specific speed, clear, right? Reflection seems to be constant. Then we see plenty of bubbles going around, right? And it seems that there is some kind of cube right? So then the question is very natural. What is this curve? Can we really define the curve that we seem to see in the center of this tube? Can we describe the tube? How does it move? What is the size of the tube? All right, and if you see here, there is on the bottom of the circle, there are seem to appear some kind of small curves. But of course, I don't know. So this is very simple. The geometry is quite elemental. Now let's change a little bit the symmetry, and let's assume that we have like a threefold symmetry. So we are going to have a curve that you could think it is invariant by rotations of angle 2 pi over 3, the plane curve. And what is the evolution? So this is another experiment. So now the evolution seems to be more involved. And by no means the corresponding curve is in the plane. It is changing, and it's probably worthy to see it again. So, for example, it is not clear what happens, at least to me, what happens at the beginning. Huh? But at some given point, it seems that you start to see what we could call the curve. And you see that it is oriented, it's kind of an axis switching with respect to the shape of the notion, right? Of course, again, what is the center? Can we define the center? What is what we are seeing around the center? Can we describe this cube? These are kind of natural questions. But then you see, it seems as if you recover the original shape, then this evolves. It goes through a period that is hard to describe. So here, probably it's also simple to see that you have the threefold symmetry, right? And then it seems that it goes back. So this is one particular example, and the one that probably was closer to the things that I described is precisely this one. Yeah? So this is a very nice experiment. It's very nice. Would create some kind of headphone, but this is done with a 3D printing. And now, in order to create the vortex, you always have to create a singularity. So if you want to create a small ring, it will never work if you push slowly the smoke. You really have to then you create. Okay? So you are starting with something which is simple. And what you really want to describe is what happens after. So in here, I guess in fact, I have even some music. These experiments were done in Chicago by guys, one that you see, and the other one, the practice is Dustin, some, I remember. So, I do think that this is one of the curves that need to be done. All right. In any case, in this case, it seems very much that the dynamics, the shape of the curve is not changing. It's just like a rigid motion. All right, so this is the plan. And the theorem, the way I see it, is that we are able to describe what at least for, say, 1/10 of the peak in the previous case. So it is not clear that it's periodic, but you could say it's more or less quasi-periodic. So we are able to describe it, say, a substantial part of this. Of course, it would be very nice to be able to describe it for the full picture. This is for the future. So now the setting is we are trying to describe fluid mechanics. So in mechanics, we have structures. In particular, one of the structures are fluid filaments, and these are places where the vorticity that I will call omega is very concentrated, right? So, and then how they form, how they evolve. This has been really the central things in the early days of fluid dynamics, and you see. All right, so mathematically, you describe the fluid by the vorticity. This is the curl of the velocity. And what you are saying is that at the given time, this is the singularity, right? Your vorticity is a vector measure because vorticity is a vector, and you describe the support to the vector. The support is given by a curve that if this chi, eventually this chi will become capital X. And this capital X is parameterized by a parameter that here will be finite parameter. And capital T is nothing but the time. So you have it. And this is the curve. I'm thinking is the kind of curve you have seen in a free. So it's a closed curve, no self intersections, very nice, right? Very smooth. This is closed, smooth curve with no self intersections. This is the set. All right, so and then so I was saying that the vorticity is the curl of the velocity that they call V, and we are in the invested case, incompressible case. I'm sorry. It's so the divergence is 0, and there is a very elemental vector calculus identity that then the curl of the curl is the amount of Laplacian, it's the diagonal matrix. The divergence is 0, so then you can use the inverse of the Laplacian together with the curve to find velocity for three known. The vorticity is, of course, it's a pretty well known, even natural guiding vector magnetism. And this is for the Biot-Savart integral or Biot-Savart law, which of course is similar. And I'm not writing here what this stands in R3, but of course, in forming a curve, this will be an integral of the field. And you can see, imagine that if this is a curve, right? Then and you are x is of course outside of the, as long as it is outside of the curve, this is fine because the integral is convergent. But as long as x becomes close to x prime, then the denominator goes like 1 over the distance squared. So if you integrate once, then you will have a singularity which will be of the type the inverse of the distance. But then I need to do a picture now. But you could think that you are working locally, so this is the curve. You have one point here of the tendency. So what you can think is that locally this will behave like a straight line, right? And then this is a computation we have all done in the total. This is what happens when the curve is precisely the gamma over 2 pi 0 to right? Then the velocity is minus x2 or minus y x0 divided by x squared y squared, and the probability is minus. So this would be the velocity field, and of course, what this thing is doing is that it's just rotating with the angular velocity, which is like the inverse of the speed, around the center. Right? So, but this would mean that the straight line remains there forever. There's no change. So, a leading order, what is going to happen is that the velocity field is going to rotate. This is in the sense what we were seeing. That it will not move the field. And in particular, in this case, where there is no curvature, so there is a perfect symmetry along all the directions in the normal plane, then nothing happens. But as soon as you have some vorticity and some curvature, then the symmetry is lost, and then you have to look at the next step. The next step will go like the inverse, the integral of the distance. So unless there is some cancellation, you will have a lot. And precisely because you have a curvature, there is no, you don't have the symmetry. So you will have a lot, right? And this is really a calculation that was done probably in this building. No, probably not in this building because it was anyway, so if I tell you when this was done. So this is what I'm saying. right? That, you can try to desingularize the integral here by using some kind of parameter of regularization parameter, which I think it is just a small neighborhood around the filament, and then you compute in powers of epsilon the leading order. So this is what you obtain. There is a log, there is a curvature, there is a gamma, so all of this before. And here all the constants go as follows. Go is what is called circulation, which is the only parameter you want. The strength of your delta. And kappa is the curvature, eventually kappa will become C, and is the binary. So at least heuristically you start to see this curvature times the binary. This, as I said, this is an old computation that was done by Rios in 1906, and he was at the time a student of Vega. And then he done work in this, at least since the time of the Rios, and you see until 1932. And in 1932, what he did was to find, say, to give kind of heuristic argument of possible curves as solutions of this binomial flow, as the one that you saw in the third. Of course, the third one is very simple, right? The third one is not so simple. Right? Okay. So, all right. So now we need to do math, and we have the. So the question is a PD question. We have the Navier-Stokes equation, so what I'm saying, for the Navier-Stokes equation, you can write it in terms of the velocity, or you can also write it in terms of the vorticity. So if you write it in terms of the vorticity, it's an initial value problem. So as long as I describe the vorticity at type 0, then I can ask if there is a solution, right? And this was solved a long time ago by Vega and Miyakawa. In 1989, as soon as you assume that the relation of gamma, the circulation, and the viscosity, so gamma divided by the viscosity, is not too big. All right? So there is a smallness condition. And why is this a smallness condition? Because what they did was to describe the solution by the fixed point argument using Duhamel formula. So the leading order is just the heat evolution of your measure, right? Okay, so this is the description they construct the solution, and this is exactly well because it is a fixed point. So this means that the solution is written as a power series. So then the leading order would be just the heat flow acting on the measure. And this is all the information they give. So in particular, they don't say in the case if it is a. So this is a general result. So the only thing you need of this measure is that if you compute the volume of the measure of balls previous R and 3D, it grows linearly enough, which of course happens here, right? Because if I would make a small of this guy, then the delta only acts in one direction, so it's growing like linear. And they compute this using the Moore reasons. So I'm saying only this is important for 2 reasons. First, I'm not going to give new solutions. But second, I'm going to construct the solution in a different way, such that I can tell you how the theorem moves. Of course, our method is more restricted than the Vega and Miyakawa method, and it is not. I cannot use it as in general. For example, I cannot put more than one filament. Vega and Miyakawa can. But by restricting these conditions, I can say more things about this.
Yes, in Vega and Miyakawa, they need smallness on gamma. Do they need some viscosity? Or
Gamma over viscosity.
so it's gamma smallness. Gamma over
Yeah.
viscosity.
No, it's gamma over viscosity. Yeah, here this is right, and viscosity is 1.
So you need this.
Of course. I mean, it's a, no, this is for Euler. No, it's gamma over the viscosity. You call it Reynolds number, you call it Reynolds number, and then that means Reynolds number is have to be. So is it clear what I'm trying to do? Good. So of course, then because you have the previous answers with to beat the heuristics, the only thing you have to find is which is epsilon. Is that you can imagine it's complicated, and it's very simple to see that the epsilon has to be a square root nu t. This is the epsilon. All right. Good. Of course, also when once you have this, you can reparameterize time by changing time, then you can make the log disappear, and then by changing the scale, you can make these constants disappear. So geometrically, this is the only thing. And in fact, when you do this, is because you are you want to describe it in geometric terms, meaning this way the curvature by normal. But really, when you do the math, this is what happens. I'm saying this because this makes sense even if the curvature is zero. In fact, to use the Frenet frame for the kind of guy I'm working with is probably not a very good idea. But it is very useful in order to understand electrically how they curve. All right. So I can take no problem in the curvature is not at all. All right. Good. So then now I'm going to give you a few references. There are plenty, and particular for fluid mechanics, probably one of the first one is the one you see on the, as number one. There is a very close connection of this question with Bose-Einstein condensates and give now, and this is, for example, the reference in the direction. Then there is a paper that I consider important for this business, which is more or less recent by Davila and White, where they really found the solution of the Navier-Stokes when you start not just with a circle, which is example just by Marquero, but by a helix. And helixes are very important in the way for reasons that we will see later. So, but I prefer to talk about particular this result. That it was, I mean, this is an important result because these people construct new solutions. So they remove the smallness condition of Vega and Vega, and they are able to construct smooth solutions, I mean, new solutions. So if you want, these are large solutions from the point of view of gamma over mu. All right. The only problem I see with this but the way they remove the big parameter is by subtracting, by saying at times small, I evolve like I fix my coordinates. What they do is something very similar to what we do, and we do something similar. We do because they started. So the game is as follows: you give your curve. And then you also have to give me, because you have such intersections, you have to give me a tubular neighborhood. Okay. Right. So that you can really make a change of variables. What kind of change of variables? I'm going to put here in this cube, I'm going to put cylindrical coordinates, where the vertical direction is going to be the time vector, and the polar coordinates will be in the normal. Correct? So you give me the curve, and it is nice at time zero, then you can construct this. And it's very easy to see that the radius has to be the inverse of the maximum of the curvature. Just by computing the minimum of the distance to the curve. Because it is close, it's compact. This is a very simple exercise. So just because I will not have time to talk about the futures, as a small exercise, what happens if you have this curve? You have a curve. Then you cannot define the uniform tubular. Right? Because, of course, this guy is of the same distance of the fluids. All right. So we are not in that situation. We are in a very nice, smooth situation. So what these people do is then I can imagine that my vortex evolves according to this guy, local. Right? And then they subtract, because you have a solution of for this, and you will write it in two slides for starting this condition for any gamma. And if you give me any viscosity, this is a free parameter. Right? So you imagine that this is your solution at time zero, it's set for very small time, and then you give the leading order, and then of course you treat the other ones as a perturbation. But you don't move the curve. So the curve is fixed at time zero. So they cannot say how it moves. Is it clear? Good. So then there is another result by Gerard Schmetz and Smith. This is an old version, because I should mention here also Gerard and Size, where they make a connection really about the binormal flow and the evolution of this. It's a general of elements. It's about existence. And the final interesting thing has happened also very recently by Vega and Vega. What they have done is really give the description when you start with the circle, gamma is as no restriction in the size of gamma in terms of the viscosity, and they do it for very large times, such that really they are able to compute the limit when viscosity goes to zero, to say that if you remove the log of mu that will appear, so you renormalize the logarithmic that appears in terms of the velocity, then it moves according to the logarithmic. But this is a fantastic result. But at the same time, it's very weak. Why? Because they don't assume swirl. So they write everything in cylindrical coordinates, assume swirl. Swirl is that you write everything in terminal in cylindrical coordinates, and then there is, so that means that you will have vectors. So you will have what we call PR, P theta, and then you will have the perpendicular direction, right? Say P. And then that means that you describe the velocity and the vorticity in terms of this frame. And there is a term that is called swirl that they are assuming is. So in mathematically, you are going back to 2 dimensions. Okay. I'm not saying this is paper is 70 pages and we have been accepted in the jobs. So this is something. But I'm saying all this to really more or less to put ourselves and you in particular, how things are going into. This is a result that has just appeared. All right? Good. So this is about the existing references. Now, what is the result we get? So now I have to describe. So remember, the starting question is: can I give you a definition of the tube? And can I give you also a definition of the center of the tube, or at least this curve that seem to appear, right? And in order to do that, I have to put myself in very coordinates, right? Or at least in some coordinates that I'm able to describe what's going on. And these are precisely the one axis. Okay, this is the first frame I use, which makes sense because, of course, this is nothing but ether. Right? It's precisely ether. So you instead of calling R as here, I call it rho because I am renormalizing through the epsilon, and this rho will be precisely this is the definition of the tubular neighborhood. Is the minimum of the distance. It is the distance, I'm sorry, given a point. So once you have the vector ER, which is precisely this one, then it computes the angular component, which is P is the vertical component. So this is pretty clear, right? This is a significant coordinates adapted to the geometry. Agree with that? Okay. So then the theorem I will describe it in terms of these coordinates. But at some point, of course, I have to use normal and boundary normal, and this would be given by this. Is it clear? All right, so, and this is the result. Okay. So, this is the really C3. So we want the curve which has not self-intersections, which is the regular C3. Torsion matters. Not just the curvature. The torsion matters. And the torsion is a derivative with respect to the curvature. Curvature is two derivatives. Torsion is three derivatives. And torsion is related to swivel. You have torsion. Right, so now this theorem is, I have my Giga Miyakawa solution, I'm going to describe it. And I describe it through the frame I have set. So the leading order is, of course, my small parameter is square root of mu t, and I'm going to describe it in terms of this small parameter. So the leading order is what we call the Lanois vortex. This was this picture, and this is. But now I have viscosity. And the viscosity, what it does, and this is a very interesting phenomena of Navier-Stokes equation in 2D, that if you start with a radial solution, then the heat flow of that solution is a solution of this, because the stretching and the in 2D you don't have stretching, but the other term is because of symmetry. So instead of having the delta, what you are going to have is the torsion. But of course, in the normal. The interesting thing here is that I have T. So it is not T equals C, as in the Russian. So I'm moving. And how do I move? I move according to the binary. All right, so you could think this is, you want linear, because it's nothing but the heat flow of the delta as a scalar. But this is completely nonlinear because it's a solution of the nonlinear. And in particular, the Michirica solution I mentioned, they are nonlinear, they are current waves. They are solving a nonlinear body. So this is a nonlinear solution. All right, and I'm saying how it's. All right, so this is the leading order, and I need to I need to say that the next term is smaller. But for purposes that will be clear in the next slide, I really need to give the next term. This is so the next term goes like the inverse of the square root of. So I have gain 1 half as long as the curvature behaves properly, which is not this. But we are in a scenario where the curvature behaves well, so I have one half powering, right? But it turns out that in order to compute this one, I really need to compute the next order, which is of the same size, but it is really nonlinear. So this is the linearization around this solution, but I really need to compute the other one. That is still in the same order of epsilon, but now it's small because of the gamma of the mu is small. You see? This is small because I'm assuming another small parameter, not the time, but the gamma. All right? Okay, why? And then once so this is my heuristics, and then I end up with the perturbation, and I do energy method. Nothing too complicated. Not even too complicated. But you know, it's more much for this. Okay? So this is done just by energy method, and you are in L2, and it's got now it's a power T, and we are computing L2. This is anything. Yeah? So this is the right power, except that this meaning this is the next order, but this is in terms of log P, we don't know if this log P should be there or not, but in any case,
Are you able in this expansion to detect the role if there is played by the sphere?
here in the evolution. I will tell you. So this is a new way of constructing the solution because it goes as follows. If you give me a solution of the binary flow, such that this picture still remains the same in the sense it can move, but I still have a tubular neighborhood which is the same for all. Then this, for example, this fits for the second example. That second example actually. And the third. Is it clear? Because you see, I'm not describing yeah, it's this is moving. So if you want the swirl in the sphere, this sphere, because it is the circle, then the cylindrical coordinates are fixed. And also in the others. Here they're moving this. So now the swirl changes. So as long as your curve moves.
Yeah, no, you told that they are able to get feeling about the viscosity at some point. They assume that.
Because it is very essentially the same.
Are you able to see?
What do you mean?
To be able to get rid of the viscosity?
No, because this is a long, small time. It's local time. Well, and this is what I need, because you see, what I'm trying to describe is how the singularity is removed, is killed by the viscosity. So at time one, viscosity has killed everything. Of course, time one means nu t equals 1. So if t is nu t equals 1 means t is smaller than 1 over nu, which is again there. Okay? Is it clear now?
But may I ask you some information for this low T, this capital T?
Yes.
Is it possible to know how big it is?
Of size 1, you want. I mean, given the gamma over nu equals 1/10, this will be 1 over 10, 10 to 10, 100.
You can compute.
Yes, you can compute. But you see, because I really want this to be the next power, I do have a small response. Right? So I cannot, so it is not completely clear that given t, I can choose gamma over nu such that something happens. Of course, if I change this power by slightly bigger direction, then the theorem is up. Given capital T, there is gamma over nu is small enough in terms of t such that all right, so yeah. So you want you remove this part, and this part you do Picard detection, and then you can compute the time. Okay? So now, of course, is this telling you is answering the question I posed? I can tell you what is the cube and what is the center. Of course, if you see this as a Taylor expansion, the answer is yes, right? Because I'm saying you can see this as a Taylor expansion. I'm telling you what is this coefficient. I'm saying this coefficient is moving according to the binary. But then you can tell me, yes, but this is the Taylor expansion at time 0. And you are trying to describe the whole thing, say, up to essentially all of them. Right? So why these are the good coordinates? If I have chosen another coordinates, maybe I can decide to go to the maximum of the vorticity, which will not be at the center, right? And then there will be a component of the curvature in the direction of the. So there is an, if you want a physical issue of what in which sense our tube is the good. And I'm going to give you a definition according to the velocity. So this is my description of the solution. So the next thing I have to do is to tell you how is the velocity.
It's like this is a kind of Taylor expansion of the solution, so that omega theta is just the remainder is encoded just by the fact that omega theta satisfies the energy inequality there. The energy inequality characterized to be the remainder in the expansion.
The remainder is in terms of powers. But that's what I was saying. You see, I'm here given an infinity condition, and here I'm given an infinity condition. But I am saying the infinity condition with a very precise geometry. So I can compute in powers of LT how the thing goes, and this is an expansion. So I can use this guy as expansion. And then it goes like in powers. So this is go like T, this will go like O of 1, and this will go like O of T. Did I answer? So then, in order to give you kind of a more reasonable definition for all time of the tube, I need to tell you how is the velocity, right? So in principle, I have a candidate to the tube and the center. So now I need to describe what are the bubbles we were seeing. right? And okay, so in order to do that, I have to first convince you what happens when so this was for when you don't have viscosity, right? This is the velocity field. So what is the velocity field when you have viscosity? So of course for the vorticity, this is what we have just computed because it's the heat flow of the delta function. And now what you have to do is to compute the inertial bar associated to this. This is a very simple calculation, very nice, and this is the answer. Remember that rho was the renormalization of the distance with respect to the parameter you see. And this is the guy. And there is a very important observation, which is that if you go to the eye of the hurricane, the eye of the tornado, this is the tornado, then the velocity, rho equals 0, is 0. So at the center, the velocity is 0. Right? All right. So now, what is the velocity in the tube, in my tube? So now it goes in powers of the inverse of t to the 1/2. This is the leading order, and this was the one that I described before. Now I have to go to the next one. And the next one, you have the bunch of terms. And of course, the leading order goes in the direction of the bottom one. I have a log. I have O of 1. I have some other terms. This one is, I will not describe, it's easily described in terms of this frame. This is the one that matters a bit more. I will describe it in the next slide. And this is lower. But let's fix here, because I want to identify my tube according to the possible trajectories of particles when the velocity field is. So as you see, the leading order of all the trajectories is 1 over the square root of t, as long as this guy is not 0. Right? And what are they doing? They are doing what we were saying before. They are rotating. So the circulation of these trajectories will be a constant that depends on the distance. Right? So if you are close to the distance, you will find this. In that sense, the center has to be down. Right? But what happens if this is 0? Then is the next slide is going to, I am going to obtain this. But that's the reason why I needed in the previous slide to say that the next order was 1 over square root of t, so that the velocity that creates is not bigger than O. And I can really see this guy. Okay, so this is my definition of the center. The center is the only trajectory such that the velocity behaves like the log of the machine. The other ones are ordered 1 over square root of t, they rotate. And this is the only one that does not rotate, it moves in the direction of the dynamo and goes as log. Okay? Is it clear? Yeah, so now this is the desingularization of the fusion. I have subtracted the leading order and I kill it, and then this is an integral. This is a convergent integral, and this is the non-local term that, of course, doesn't, you don't know what it goes. No, unless you don't have a global symmetry, for example, in the case of the circle, you can see. All right, so we computed really the non-local. So this is a new one, and I haven't studied this yet. For example, this is a very nice proper question. Imagine that my curvature is small. In the case of the circle, curvature small means that the circle is very big. So is this of size of the L infinity norm of the curvature instead of L1? So you have an integral. This is we don't know, and this is of course. Anyway, so now let me see. This is the. So I have still what 10 minutes or so. Okay, so this is where we are, right? Except that I haven't told you. Okay, this is fine, but give me solutions on the binomial form. right? Because it was if I have a solution, then I can do it. And this is, of course, there is plenty of, in order to do that, I have to speak about the relation between this guy and two other guys. One is what is called the Schrödinger map, which is the equation that the capital T was the tangent of the curve that in our language is the direction of the vortices. It is a very natural quantity that appears in Euler and Weierstrass, particularly related to the Constantin-Pfeffer-Maida condition. It's precisely the variation of the direction of the vorticity, the one that controls the global. And the variation of tangent vector is the curvature. All right? So this is an important time. So really you want to understand things in terms of curvature and torsion, and here is where now the curvature is not kappa, it's C. All right? This is the binormal frame, and so this is the Frenet frame, and then you can use this to prove that the straight lines, circles, and helices are fun. In particular, helices are traveling waves at the time. It's a very simple and nice. You go to the equation of capital T that you just obtain it by. So to go from here to here is just to differentiate when the derivative of here is 0. So then this is what you get. And if you assume now that T is a traveling wave, you immediately obtain helices. But of course, helices are not produced. So in principle, I cannot use this. But then you can do different things. Let's start from the most complicated one, which is a fascinating or an amazing connection between this Schrödinger map and the binomial flow in terms of cubic NLS. This, in fact, I learned about this when I was in a conference organized by Toru Osawa in Sapporo, and it was Konio. Oh. Konio was the guy. Yeah, no. I'm sorry. I don't. It's in the proceedings, in fact. Okay. So then, amazingly, you obtain the cubic NLS, but it is not just the usual cubic NLS because it's a geometric one. So you have a free parameter, which is the gauge. Of course, you have the freedom of either using the Frenet frame or any other frame that is good for your purposes, and this is important, but not for the thing, not for today, except that gives you an extra. All right. So then you could think that solutions of this problem. So now I'm looking for closed curves, so that means I will need periodic solutions in the side, because the sign describes the curvature of the torsion, so I need curvature periodic and torsion periodic, but even more than that, because I need the whole thing to be closed. So these are natural conditions for cubic NLS, and of course you have the results by David Civica is the one I told you that he was not aware of this connection, but what he did was to write a curve in terms of curvature and torsion, and he found a system that in fact this is as if you go here and you write the polar coordinates, what is the equation for the C and the tau, and then you try to find solutions. That's what Levi-Civica did. All right. And then really the result, the general result for the theorem I need is, for example, the one by these people, Schlemsler and Bardos. The L2 case for the full line is by Susumi. The one I need in principle is the one I will get because that's in periodic. But in any case, all these ones, at least the one by Susumi and the one by Gauguin, and this one also will tell me anything about the geometry in the sense that how can I be sure that you don't have self-intersection? It is very important. So then I need more explicit things, and this was done by Kida in 81 by looking at, and this will be the next slide. And this Kida, the solution given by Kida, it has been generalized recently by Claudia Garcia and myself in the paper that will appear this year. So now you're sure. So this is what Kida does. Let's assume that you have a rigid motion. And you have the parameters, which is translations around the filament, rotations in the perpendicular plane, and just the velocity, say, in the perpendicular direction. So you're fixing here really significant coordinates, but you're adding these rotations, and you're moving. Okay? And this can be, there is no reason why it has to be planar. This can be different. So then you do the math. this is cylindrical coordinates again, and you end up in a very well-known ODE, which is the cubic elliptic equation in 1D, which is complex. You look for traveling solutions, and really you can explicitly compute the solutions in terms of elliptic functions. And then you have a bunch, right? And then for many of them, you can say they are periodic and they are not self-intersecting. In particular, for the third one, okay. Of course, now we have two new parameters, A and omega. That, for example, in the case of the physics, is the period and the pitch and the torsion and the curvature. These two parameters are new for navigation. So you have the gamma, you have the viscosity, and now you have these two new parameters. Of course, the theorem I gave you is just when these two parameters are of size 1, because I was assuming C3, right? So you want the torsion, which is equivalent to the fluid you want. I am assuming it's controlled. But it's something that, of course, we are working on is how our theorem depends on these new parameters. I still can assume that the gamma over mu over viscosity is of size 1. But can I make these parameters big? Okay. This is what we are working on. And just to finish is what would be the future? For example, the future for me would be really, I want to describe this. And because again, Vega and Miyakawa construct the solution for this, also for this. And we don't know what is the dynamics. We expect the dynamics to be the one you see there. This is a very old paper. Huh? It's 1978. And these are what are called the coherent structures. It's like typically when you go to the books or to the description in fluid mechanics, mainly by engineers, they tell you this is a laminar flow and this is structurally turbulent. But it is not completely turbulent because you still see some structure. Right? Which are these structures? How are they moving? Okay. Of course, now for me it's not clear at all that this is laminar. I really would like to know what happens there. Because you see, when you see the structure, it's already developed with a given size. In particular, if this should be connected to the binormal flow, this is what we don't know. This should be the canyon. And now you have the horseshoes, you have it for all the scales. While in the previous picture, it seems that you only see the guy at a given distance. So, why is this so important for me? Because by using this, you can really do very complicated things. In particular, there is plenty of literature also concerning the description of turbulence, for example, intermittency, as based on the interaction of vortex filaments. It's very natural to think that you can do it. There are many papers that they say that it's not enough to look at the interaction of filaments or even one filament, whatever, to explain intermittency. In particular, there is this paper. Arneolo is and he was a collaborator of in fact, Jafar started to work on turbulence, that's what Jafar told me, that he started to work on things related to turbulence of fluid because Arneolo insisted in. And of course, these people come from the major school on the wavelets, and wavelets at the very beginning were very successful describing turbulence. At least it was a step forward. But this step forward was not enough. And this is what this paper says. And in the school of Meyer and Jafar, they soon realized that if the singularities that appear are not just Holder type, that are very well described by wavelets, meaning that you really have singularities created by oscillation, what they call chirps, then wavelets are not. Okay? And this is what this paper says, that if the only singularities you have are of the Holder type, then the vortex filaments will not be enough to describe intermittency. But of course, in the previous picture, This is precisely the kind of oscillating thing we want to. You see, these are my helices. This is the transport of energy are created by these helices. So these guys play a fundamental role. And in fact, when you go to the fundamental solution, this is the picture you have seen. This is the solution of the binormal flow that just started with the coordinates. We have a very precise description of the solution, right, which is this. And you have this term, which is the normal, and the normal has these oscillations. And of course, this is similar. So you fix S, this behaves like S squared over 4t. So this is really a definition of the chip. So this is the reason why for me this is so relevant to know if the solution constructed of Vega and Miyakawa for this type of initial condition is described by the solution. Because it is not a question about interaction of filaments, it's a question about how many corners you have. And I will finish with this move. Right. So this is the evolution of the binormal flow for two types of curves. In the bottom, what you see is the circle. And of course, what we are going to see is that it moves in one direction, so it goes up. And I will put in one dot. So the trajectory will have to be a straight one. Right? This is what you are going to see in the circle. The one on the top is just a polygon with 15 sides, regular. Right? And then I will put in one of the vertices, and I will try to describe the trajectory. Right? So this is what you see. Of course, trajectory in the case of the regular polygon is much more. Right? This complicated trajectory becomes smaller and smaller with the number of sides. That makes sense. But that means that, in any case, if I do the sum that the skating tells me how to do it, this is one of the new parameters I'm adding. Have this three parameters. If I add this sum, what I obtain is a guy that does not disappear. This guy is well known and is generated by what is called the Riemann's non-differential loss, which is generated by the one I mentioned. All right, so this is the question I was saying at the beginning that now I would like to know the answer. I don't know what will be the answer, but whatever the answer is, it will be interesting. That's my question. So I don't know, of course, if this has anything to do with the picture we saw at the beginning. All right, so, and what I'm saying is that this trajectory you see from this super box is generated very easily by this Fourier series. We just have to use n here is 15. This has to be a very precise number that we know what it is, and then you just to fix the vertex is to make x equals 0, and then you compute the trajectory, and this is what you have seen when n equals 50. And I have n. Okay.
Thank you, Luis, for the interesting photo. So, is there a question?
Yes.
Okay, so the question is why should the binomial flows be related to models like this? Because I mean, at least looking to the pictures you showed in the last slides. So it seems that this kind of situations want to create many chaotic.
Let's see the
binomial flows.
let's see the trial. Okay.
This is the binomial.
And what do you see there? This is locally it's precisely the and this is a theorem. You see what happens is that this corner immediately creates all these waves. But because it is closed, they start to interact. And this is the we start to have plenty of resonances which are complicated and eventually they don't. So again, for me, it's like I only need really because this is a multi-factor. I only need to understand the description here. Where you in principle don't see anything. We need T small. And what I'm saying is that for T small, what I see here is the subsymmetry. I don't know if that was.
This is the binormal flow.
Yes.
But then, if you go back to the pictures in which you see the smoke,
Yes.
you see that there are physical behaviors like chaoticity, ergodicity, which are not encoded in this kind of data. This is like
I'm not trying to describe all of it. I'm not trying to describe all of it. What I'm trying to describe is at least a particular scenario where I can see intermittency and if you want multifactoriality in the setting of fluid mechanics that fits with the experiment. And what I am suggesting is that they start with the space, the lateral triangle or square, put viscosity as small as you want, if you can. And can you see these guys on?
how far I need to do this for the corner.
I don't know. But the same exists and it's completed by the resistance is there. It's done by the calculation. So should be there. Whatever it is should be there. Of course, the question is, do I need viscosity to be small to see the value? And I don't think so, because I can make this angle as close to bias. And I still have the same kind of communication. That is the polygon, you see? Even if I increase the number of sides of the polygon, that means that the angle is becoming closer and closer. But if I do the corresponding zoom, I see it. All right? So, all right?
Probably one small thing connected with the fact that initial movie that you show, I'm really very interested what will happen when the curve hits a wall. When it hits, this
No.
will appear immediately. This
No, it's the other way around. I'm not describing the creation of singularities. The singularity has been created at time zero. What I'm describing is how this singularity desingularizes. And what I am saying, you see, is the way I see it is precisely again the same movie. What you want here? You have the singularity immediately. The curve becomes regular, but creates all these waves that they start to interact and have a closed polygon. So the question is, do I have enough time such that these oscillations start to create resonances? And the time goes like the inverse of the viscosity. And the velocity of these guys go depending on the parameters I'm saying. So I have the freedom of these two.
is the opposite process.
Yeah, so it is the opposite process. Huh? Of course, I'm not creating singularities. The only thing I'm trying to say that I can create complicated dynamics. I'm not pretending to win $1 million. Huh?
So your message is for very small time, the good candidate, so for very small time, where you don't see any, like when you see any relevant phenomenon physically, the candidate is the Vega. Describe up to maybe the second law.
But this is what about intermittency and turbulence is. It's not a big amplitude things. It's that the velocities, the histograms, the probability densities of the velocities are a mess. You don't know what they are. So it is not about the size, it's about the fluctuation. It's like imagine that I put myself in this is the trajectory, right? I am following the trajectory. At the beginning, the fluctuations are very small. But if I zoom, it is a real mess. I mean, the amplitudes are very small, but the fluctuations are big. The amplitudes, I'm following a straight line. But if I look at the small scale, it's crazy. All right? So I can have complicated dynamics without creating singularity. The different question is who creates the equilateral triangle as a starting time. That's a different issue.
Other questions? Okay, if not, we can thank Luis again.